The nothing before the universe is different in kind from any nothing you have ever experienced or imagined. It is a nothing so complete that there is no space in which something could exist, no time in which something could happen, no laws of physics waiting to be applied, because the laws of physics are themselves something, and something had not yet happened. No darkness, because darkness requires space to be dark in. No silence, because silence requires time in which sound could have occurred but didn't. Not emptiness, the absence of the possibility of emptiness. This is the hardest thing in all of physics to hold in the mind, and the most honest thing to say about it is that the human mind may not be capable of holding it. The mind evolved on the surface of a planet that has always existed, in a universe that has always existed, for the purpose of navigating a world that has always existed. The concept of a time before time, a space before space, a state before states existed. These are not concepts that natural selection equipped you to understand intuitively. They are concepts that require an act of deliberate, cognitive effort that goes against every default assumption your brain makes about the nature of reality. So we will approach them slowly. We will approach them the way you approach anything that is difficult and important, not by demanding immediate comprehension, but by circling the idea, looking at it from different angles, letting it settle in the way that ideas settle when you give them time and quiet. We have time tonight, and we have quiet if you let the room become what it is. The universe began approximately 13.8 billion years ago. That number, 13.8 billion years, is so large that it defeats the imagination that tries to grasp it directly. We will need to come back to it many times, from many angles, before it begins to mean anything. For now, just hold it as a fact, the way you hold any fact before you understand it. 13.8 billion years ago. A specific moment in time, as specific as any other moment, as specific as the moment you read this sentence, except that it is the first moment, the moment before which there were no moments, the event before which there were no events. The cosmologists call it the Big Bang. The name is unfortunate in some ways. It suggests an explosion, something going bang, in the colloquial sense, something going from here to there with a loud noise and a flash of light. But the Big Bang was not an explosion in space. It was an expansion of space itself. And there was no bang, because there was no air to carry sound, and there was no outside observer to hear one. There was simply and suddenly, and from a state of incomprehensible density and temperature, the beginning of everything. Tonight, we are going to follow that beginning from its first instant to the present moment. From the Planck era, the first unimaginably brief fraction of a second when physics as we know it did not yet apply, through the formation of the first particles, through the first atoms, through the first stars, through the first galaxies, through the formation of our solar system and our planet and the emergence of life, all the way to this moment, this room, this breath. It is the longest journey you will ever take. It begins before time. Let us begin. Find your position, the one you intend to keep. Let the day release its hold on you. If these journeys mean something to you, the subscribe button is there. A comment telling me where in the world you are listening from tonight is something I always find myself glad to read. The universe is about to begin. The first thing to understand about the Big Bang is what it was not. It was not an explosion in the sense that the word explosion normally implies. An explosion, in ordinary usage, means a rapid release of energy in a pre-existing space. A bomb detonates in air, shrapnel flies outward, pressure waves spread through a medium that was already there. The Big Bang was not like this. There was no pre-existing space for it to explode into. There was no surrounding emptiness waiting to receive the energy. Space itself, the very fabric in which things can be located and through which things can move, was created in the Big Bang. The expansion of the universe in the moments following the Big Bang was not matter moving outward through pre-existing space. It was space itself expanding carrying matter with it. This distinction matters because it changes everything about how you visualize what happened. If you imagine the Big Bang as an explosion in pre-existing space, a fireball expanding outward from a central point into an already existing void, you will be wrong in a way that causes confusion about almost everything that follows. The universe does not have a center from which everything is moving outward. It does not have an edge beyond which there is empty space that the matter has not yet reached. The universe is not expanding into anything. Space itself is expanding, and every point in space is moving away from every other point. The way dots on the surface of a balloon move away from each other when the balloon is inflated, not because any dot is at the center, but because the surface itself is growing. Imagine you are one of those dots. From your perspective, every other dot is moving away from you. You might conclude that you are at the center of the expansion, but a dot on the other side of the balloon would reach the same conclusion, and both conclusions would be equally wrong. There is no center on the surface of a balloon. There is only the surface, and the surface is expanding. The universe is like that, except in 3 spatial dimensions rather than 2, and just as there is no center on the surface of a balloon, there is no center of the universe. Every galaxy is moving away from every other galaxy, not because they are all flying outward from a common point, but because the space between them is expanding. This is the first thing to understand, and it is genuinely counterintuitive, and it is all right if it does not feel fully understood yet. Let it sit. We will return to it. The second thing to understand is that the Big Bang was not just the origin of matter and energy. It was the origin of space and time themselves. Time, as Einstein taught us, and as the equations of general relativity express with extraordinary mathematical precision, is not a fixed and external stage on which events occur. Time is itself a physical quantity, part of the fabric of the universe, shaped and influenced by the matter and energy that inhabit it. Gravity bends time the way it bends space. Velocity affects the rate at which time passes. Time and space are not separate things, but aspects of a single 4-dimensional entity that physicists call space-time. If time is a physical quantity, then it had a beginning. The Big Bang is not just the beginning of the universe in the sense of the beginning of matter and energy. It is the beginning of time itself, the point at which the concept of before ceases to be meaningful. There was no time before the Big Bang, not because something prevented time from existing before it, but because time began at the Big Bang the same way that space did. Asking what happened before the Big Bang is, in a precise technical sense, like asking what is north of the North Pole. The question sounds meaningful but contains a category error. It applies a concept, before, to a situation in which that concept has no referent. This is the second thing to hold, and it is perhaps even harder than the first. There was no time before the Big Bang, not because time was prevented from existing, but because time itself began there, with space, with matter, with energy, with the laws of physics, all of it together, at once, from a state of conditions that we do not fully understand and perhaps cannot, in principle, ever fully reconstruct. The third thing, and this one we will spend much of tonight working through, is that we know the Big Bang happened, not as a hypothesis, not as a guess, not as the preferred creation story of a particular scientific culture. We know it happened because the universe contains specific, measurable, reproducible physical evidence that it happened, evidence so consistent and so detailed and so precisely predicted by the theory before it was observed that the alternative explanations require assumptions so complex and so unsupported that they are, in the judgment of essentially every physicist who has studied the question, untenable. The universe is expanding. The cosmic microwave background radiation fills all of space with a uniform glow that is the cooled remnant of the early universe's fire. The abundance of helium and hydrogen and the trace elements produced in the first few minutes matches precisely what the Big Bang theory predicts. The large-scale structure of the universe, the way galaxies cluster and filament and form the great cosmic web, matches the predictions of cosmological models based on the Big Bang with extraordinary accuracy. We did not invent the Big Bang to explain the universe. We discovered it because the universe kept insisting on it. The year is 1929, and an astronomer named Edwin Hubble is looking at distant galaxies through the 100-inch Hooker telescope on Mount Wilson in California. Hubble has already established something remarkable, that the fuzzy patches of light that his predecessors had called nebulae and had assumed were clouds of gas within our own Milky Way galaxy are in fact entire galaxies in their own right, vast collections of hundreds of billions of stars, so far away that even their individual stars are invisible, and they appear as mere smudges of light. The universe, Hubble has shown, is incomprehensibly larger than anyone had previously understood. The Milky Way, which had seemed to be essentially the whole of the visible universe, is just one galaxy among billions, perhaps among hundreds of billions. But now Hubble is looking at something else. He is looking at the spectra of these distant galaxies, the way the light from them is distributed across different wavelengths, and he is noticing something that he and his colleagues will spend years trying to fully understand. The light from almost every distant galaxy is redshifted. Redshift is a phenomenon that any physics student knows. When a source of waves, whether sound waves or light waves, is moving away from an observer, the waves are stretched, their wavelength increased. For sound, this produces the lowering of pitch you hear as an ambulance passes you and drives away. For light, the stretching of wavelength shifts the light toward the red end of the spectrum. A galaxy whose light is redshifted is a galaxy that is moving away from us, and almost every galaxy Hubble looks at has redshifted light. More than that, the further away a galaxy is, the more its light is redshifted. The further away, the faster it is moving away from us. Hubble has discovered that the universe is expanding. Every galaxy is receding from every other galaxy, and the speed of recession is proportional to the distance. This relationship, now called Hubble's law, is one of the most important empirical findings in the history of science, and its implication is one of the most profound thoughts in the history of human understanding. If every galaxy is moving away from every other galaxy, then in the past, all galaxies were closer together. Run the expansion backwards, the way you rewind a film, and you arrive at a moment when all the matter and energy in the observable universe was compressed into a state of extraordinary density and temperature. Keep running it backwards, and you arrive at a point of infinite density, what physicists call a singularity, that is the origin of everything. Hubble did not immediately draw this conclusion himself. The Belgian priest and physicist Georges Lemaitre had already proposed it 2 years earlier, in 1927, working from the equations of Einstein's general relativity. Lemaitre called it the hypothesis of the primeval atom, his proposal that the universe began from a single, incredibly dense state that he imagined as a kind of primordial atom containing all the matter and energy of the cosmos. It was a remarkable piece of theoretical reasoning, and it was largely ignored until Hubble's observations provided the observational evidence that the theory demanded. Einstein himself had resisted the implication. His general theory of relativity, when applied to the universe as a whole, naturally produced solutions describing an expanding or contracting universe. Einstein found this aesthetically unacceptable. He believed the universe should be static, eternal, neither expanding nor contracting. To force his equations to produce a static solution, he introduced a term called the cosmological constant, essentially an additional force that counteracted gravity on large scales, that he later described as the greatest blunder of his life. When Hubble's observations made the expansion of the universe undeniable, Einstein abandoned the cosmological constant and accepted that his original equations had been right all along. The universe is dynamic, not static, and it is expanding. The expansion of the universe was the first great clue. It tells us that the universe had a beginning, but it tells us almost nothing about what that beginning was like, or what happened in the moments immediately following it. For that, we need to go back much further. Back past the first galaxies, past the first stars, past the first atoms, all the way to the first fraction of a second. The universe is 13.8 billion years old. Let us go back to the beginning. Not to the very beginning, we will work up to that, but to the first few minutes, when the physics was already recognizable, but the universe was still unimaginably different from what it is today. In the first few minutes of the universe, the entire observable universe, all the matter and energy that will eventually become every galaxy, every star, every planet, every living thing is compressed into a volume smaller than the present-day solar system, at a temperature of billions of degrees. Billions of degrees. Not the temperature of a bonfire, which is measured in hundreds of degrees. Not the temperature of the surface of the sun, which is about 5,800 degrees. Not the temperature of the sun's core, which is about 15 million degrees. Billions of degrees, a temperature so extreme that the very concept of individual atoms is meaningless, because atoms cannot hold themselves together at those temperatures. The energy is so high that electrons are stripped from nuclei as fast as they can combine with them. The universe is a plasma, a dense, hot, opaque soup of charged particles moving at nearly the speed of light, interacting with each other through all four of the fundamental forces at energies that our most powerful particle accelerators can only approach, never fully match. This state, dense, hot, uniform, is not the very beginning. It is already the universe several seconds old. Several seconds is a long time in cosmological history, especially in the first few seconds, when the universe was changing rapidly. We need to go back further. But first, let us watch what happens as those first few minutes play out, because they are some of the most consequential minutes in the history of everything. The universe is cooling. This is the fundamental dynamic of the early universe expansion and cooling. As space expands, the energy in it is distributed over a larger volume, which means its temperature drops. The relationship between expansion and cooling is governed by precise equations that physicists can solve, and the predictions those equations produce can be tested against observations, and they match with extraordinary precision. At 1 second after the Big Bang, the temperature is approximately 10 billion degrees. The universe contains a dense mixture of photons, particles of light, electrons, positrons, the antimatter equivalents of electrons, neutrinos, ghostly particles that barely interact with anything, and protons and neutrons, the particles that make up the nuclei of atoms. Something important is happening at this temperature. Protons and neutrons can interact through the weak nuclear force, converting into each other. A proton can absorb a neutrino and become a neutron, or emit a positron and become a neutron. A neutron can do the reverse. These conversions are happening rapidly in both directions, and the ratio of protons to neutrons is determined by the temperature and the mass difference between the two particles. This matters enormously because it sets the stage for something that will happen in the next few minutes. The first and most consequential chemistry in the history of the universe. At about 1 second, the temperature has dropped enough that neutrinos are no longer interacting rapidly with other particles. They decouple essentially. They stop interacting with the rest of the matter and radiation and begin to stream freely through the universe, a cosmic neutrino background that still permeates all of space today, though we have never directly detected it because neutrinos interact so weakly with ordinary matter that detecting them is extraordinarily difficult. At about 3 minutes after the Big Bang, something happens that cosmologists call Big Bang nucleosynthesis, and it is the beginning of chemistry in the cosmic sense. At this moment, the temperature has dropped to about 1 billion degrees, still incomprehensibly hot, but cool enough for an important new thing to happen, cool enough for protons and neutrons to stick together. A proton and a neutron can combine to form a nucleus of deuterium-heavy hydrogen, a hydrogen isotope with one proton and one neutron. At the temperatures of the first second, any deuterium nucleus that forms is immediately destroyed by the high-energy photons that fill the universe. But at 1 billion degrees, the photons have cooled enough that some deuterium nuclei can survive long enough to participate in further reactions. And further reactions happen rapidly. A deuterium nucleus and a proton combine to form a helium-3 nucleus. 2 helium-3 nuclei combine to form a helium-4 nucleus. Some helium-4 nuclei combine with deuterium to form trace amounts of lithium-7. This process, the building of light atomic nuclei in the hot early universe, lasts for only about 17 minutes. At the end of that 17 minutes, the temperature and density have dropped below the threshold at which nuclear fusion can proceed, and the composition of the universe is essentially fixed. The composition is specific. By mass, the universe is approximately 75% hydrogen and 25% helium, with trace amounts of deuterium and lithium. This is a precise prediction of Big Bang nucleosynthesis theory. And when astronomers measure the composition of the oldest and most pristine objects in the universe, the most ancient stars, the gas clouds that have been least affected by stellar processing, they find exactly this composition: 75% hydrogen, 25% helium, traces of deuterium and lithium. This match between theory and observation, between the prediction made from the physics of the first 3 minutes and the composition measured in the oldest objects in the universe, is one of the most stunning confirmations in the history of science. The Big Bang Theory does not just predict that the universe began hot and dense. It predicts, with precision, the specific chemical composition that a universe beginning hot and dense should have. And the universe has that composition. The first 3 minutes made almost everything that the first stars and galaxies were made of. Hydrogen and helium, built in the first few minutes, are the raw material from which the first cosmic structures were assembled. Everything heavier than helium, the carbon in your body, the oxygen you breathe, the iron in your blood, the calcium in your bones, was made later, in the nuclear furnaces of stars, and distributed through space when those stars died. But the hydrogen that makes up the bulk of all matter in the universe, the hydrogen that was in the early ocean we explored in another journey, the hydrogen that is in the water moving through your body right now, that hydrogen was made in the first minute of the universe's existence, in the Big Bang nucleosynthesis that produced the building blocks of everything. Now let us go back further, past the first minutes, past the first seconds, into the first fractions of a second, where the physics becomes stranger and our understanding becomes less complete. At 1/10 of a second after the Big Bang, the temperature is approximately 300 billion degrees. At this temperature, protons and neutrons are themselves barely stable. The quarks and gluons that make them up are so energetic that they are constantly being created and destroyed in particle-antiparticle pairs. The universe a seething foam of matter and antimatter appearing and annihilating in equal quantities. The quarks come in 6 types, called flavors by physicists with a sense of humor that their subject demands: up, down, charm, strange, top, and bottom. Ordinary matter, protons and neutrons, is made of up and down quarks. A proton is 2 up quarks and 1 down quark, bound together by gluons, the particles that carry the strong nuclear force. A neutron is 2 down quarks and 1 up quark. At the temperatures of the first fractions of a second, all 6 quark flavors are being created from pure energy and annihilated back into energy in a continuous churning. The universe is not made of protons and neutrons yet. It is made of quarks and gluons and leptons, electrons and their heavier cousins, and the associated neutrinos and photons and antimatter counterparts of all of these, a state called the quark-gluon plasma that Physicists have recreated in particle accelerators by smashing heavy atomic nuclei together at nearly the speed of light. At about 1 microsecond after the Big Bang, 1/1,000,000th of a second, the temperature drops enough for a phase transition to occur. The quarks condense into hadrons, the class of particles that includes protons and neutrons, in a process called the quark-hadron transition. This is the moment when matter, in the sense we recognize it, first appears. Before this transition, the universe contains a quark-gluon plasma. After it, the universe contains recognizable particles, protons, neutrons, and their antimatter equivalents embedded in a dense gas of photons and leptons. At this moment, something happens that will define everything that follows, and that remains one of the most profound mysteries in physics. When a particle and its antimatter equivalent meet, they annihilate. They convert entirely into energy, into photons, into pure radiation. If the universe had produced exactly equal amounts of matter and antimatter in the quark-hadron transition, then all the matter and all the antimatter would have annihilated, and the universe would contain nothing but radiation. No protons, no neutrons, no atoms, no stars, no planets, no life. The universe we observe does not contain equal amounts of matter and antimatter. It contains overwhelmingly more matter than antimatter, so much more that essentially all of the antimatter was annihilated in the first second, leaving a residual excess of matter that went on to become everything. The ratio is approximately 1,000,000,001 matter particles for every billion antimatter particles, a tiny asymmetry that, multiplied by the annihilation of a billion matched pairs, leaves the one extra matter particle for every billion pairs. That tiny asymmetry, 1 part in a billion, is everything. Everything you have ever seen or touched or thought about is made of that residual matter, the tiny excess that survived the great annihilation of the first second. Every atom in your body, every molecule of the air, every star in the sky, every galaxy in the observable universe, all of it is the 1 in a billion surplus from the great matter-antimatter accounting of the first second of the universe. Why did this asymmetry exist? Why did the universe produce slightly more matter than antimatter? This is called the baryon asymmetry problem, and it is one of the great unsolved questions in physics. The standard model of particle physics, our best current theory of the fundamental particles and forces, does contain mechanisms that could produce a matter-antimatter asymmetry, but it cannot produce an asymmetry as large as the one we observe. Something in the physics of the very early universe produced the small, crucial imbalance that allowed everything to exist, and we do not fully understand what it was. The universe, it seems, cheated slightly in favor of matter, and everything in existence is the consequence of that small cheat. Now let us go back further still, to the very first microsecond, to the first fraction of a microsecond, into the realm where our best physical theories begin to strain and ultimately break down. The first thing to understand about this era is that it is genuinely, fundamentally beyond direct observation. The cosmic microwave background radiation, the oldest light in the universe, which we will discuss in detail shortly, comes from approximately 380,000 years after the Big Bang. Before that, the universe was opaque. The photons were so densely packed and interacting so frequently with charged particles that light could not travel freely. The universe before 380,000 years is hidden behind a wall of opacity that no electromagnetic radiation can penetrate. To know what happened in the first fractions of a second, we must rely on theoretical physics, on the equations of particle physics and cosmology, on what we can infer from the properties of the universe we observe today. We cannot see those first moments directly. We can only reason toward them. What we can reason toward is extraordinary. At 1/1,000,000th of a billionth of a billionth of a billionth of a second, at 10 to the power of minus 43 seconds, we reach what physicists call the Planck time. The Planck time is the smallest meaningful unit of time in our current physics. Below this scale, Our theories of physics, both quantum mechanics and general relativity, break down. They produce infinities and nonsensical results. The mathematics ceases to give meaningful answers. The Planck time is named after the German physicist Max Planck, whose work in the early 20th century laid the foundation for quantum mechanics. The Planck scale, the scale defined by the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant, is the scale at which quantum effects and gravitational effects are both significant simultaneously. It is the scale at which a theory of quantum gravity is needed, and we do not have a complete theory of quantum gravity. At the Planck time, the temperature was approximately 10 to the power of 32 degrees, a number so large that writing it out in full would require more zeros than this script contains words. The density was approximately 10 to the power of 94 grams per cubic centimeter, so dense that all the matter in the observable universe was compressed into a volume roughly 10 to the power of negative 99 centimeters across, a volume so small that it makes a proton look vast. At the Planck time, all four of the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. They were not four separate forces, but a single superforce, a single interaction, governed by a single set of physical laws. This is the state that physicists call the grand unified phase, and while we have no complete mathematical description of it, the evidence that it existed comes from the way the forces behave at high energies. As the energies accessible to particle accelerators increase, the strengths of the different forces converge. The strong force weakens, the electromagnetic and weak forces strengthen, and their coupling constants approach a common value. Extrapolate to the energies of the early universe, and the forces unify. Then, at the Planck time, something happens. Something leaves the Planck era and enters a slightly later era, still unimaginably brief, that we call inflation. Inflation is the most dramatic and least understood chapter in the history of the early universe, and it is the key to almost everything about the large-scale structure of the cosmos. The theory of cosmic inflation was proposed by the physicist Alan Guth in 1980, and it addressed several puzzling features of the observed universe that the straightforward Big Bang theory could not explain. The first puzzle is called the horizon problem. Look at the cosmic microwave background radiation, the faint glow of microwave radiation that fills all of space uniformly, the afterglow of the Big Bang's fire. It is extraordinarily uniform. The temperature of the cosmic microwave background is the same in every direction you look, to better than 1 part in 100,000. Left and right, up and down, north and south, the temperature is the same. This is a problem, because the regions of the sky that are in opposite directions, say, the point directly overhead and the point directly below your feet, are so far apart that, in the standard Big Bang model without inflation, they could never have been in causal contact. Light could not have traveled from one to the other in the time available. In the standard model, these regions were never connected, never able to exchange heat and energy, never able to come to thermal equilibrium, and yet their temperatures are identical to better than 1 part in 100,000. How can regions that were never connected be at the same temperature? In ordinary experience, regions come to the same temperature by exchanging heat. A hot object and a cold object, placed in contact, will eventually reach the same temperature, but only if they are in contact, only if heat can flow between them. If they were never in contact, they should have different temperatures. The second puzzle is called the flatness problem. The geometry of the universe, whether it is positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a flat plane, is determined by the density of matter and energy in it. Physicists define a critical density at which the universe is exactly flat. If the actual density equals the critical density, the universe is flat. If it is greater, the universe is positively curved. If it is less, the universe is negatively curved. Measurements of the geometry of the observable universe show that it is extraordinarily close to flat. The density is within 1% of the critical value. The universe is not exactly flat, perhaps, but it is very close. And this is a puzzle because in the standard Big Bang model, exact flatness is an unstable condition. A universe that begins even slightly above or below the critical density will diverge rapidly from flatness as it evolves. For the universe to still be this close to flat today, after 13.8 billion years of evolution, it must have begun extraordinarily close to flat, fine-tuned to better than 1 part in 10 to the 60th. This seems to require an extraordinary and unexplained coincidence in the initial conditions of the universe. The third puzzle is the absence of magnetic monopoles. Grand unified theories of physics predict that the very early universe should have produced vast quantities of exotic particles called magnetic monopoles. Particles that are, essentially, isolated magnetic poles, the North Pole without a south, or vice versa. These particles should be stable and should persist to the present day. They should be everywhere. And yet, no magnetic monopole has ever been detected. Inflation solves all 3 of these problems in a single stroke. The inflationary theory proposes that between approximately 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, an interval so brief that it is difficult to express meaningfully in human terms, the universe underwent a period of exponential expansion. Not the gradual expansion that has continued from the Big Bang to the present, but a sudden, dramatic, exponential expansion, the universe doubling in size every tiny fraction of a second, inflating by a factor of perhaps 10 to the power of 26 or more, in an unimaginably brief interval. Before inflation, the entire observable universe was compressed into a region smaller than a proton. All of it was in causal contact, connected, thermally equilibrated, at the same temperature. Then inflation took this tiny, uniform, connected region and blew it up to cosmic scales, preserving the uniformity while separating its different parts by distances too large for light to bridge. The horizon problem is solved because the regions that appear causally disconnected today were, before inflation, causally connected. Inflation also solves the flatness problem. Any curved surface, inflated by a factor of 10 to the 26, becomes locally indistinguishable from a flat surface. Think of the surface of the Earth. It is clearly curved, but if you look at a small patch of it, it appears flat. Inflation took whatever geometry the pre-inflationary universe had and stretched it to such enormous scales that the remaining observable universe is a tiny flat patch on a much larger, possibly curved whole. And magnetic monopoles? Any monopoles produced before inflation would have been diluted to such low densities by the expansion that the probability of finding one in the observable universe is essentially 0. They exist, probably, somewhere in the enormously larger volume of space beyond what we can observe. But in our corner of the inflated universe, they are effectively absent. Inflation is an extraordinarily powerful and economical explanation for 3 separate puzzles, which is one of the reasons physicists take it seriously, despite the fact that we do not yet have a complete, agreed-upon version of the theory. The basic idea, a period of exponential expansion in the very early universe, seems to be correct. The specific mechanism that drove this expansion, the nature of the field that caused it, called the inflaton field, in a naming convention that reflects the physicist's preference for clarity over elegance, and the detailed dynamics of its beginning and end, these are still subjects of active research and debate. One of the most remarkable predictions of inflation is that it should have produced a spectrum of tiny quantum fluctuations, ripples in the density of the early universe, generated by the inherent quantum uncertainty of the inflaton field, stretched to cosmic scales by the inflationary expansion. These tiny density fluctuations are the seeds of all the structure in the universe. They are the small variations in density from which, Under the influence of gravity, the first stars and galaxies eventually grew. And their statistical properties, the specific mathematical relationship between fluctuations at different scales, can be predicted by inflationary models and tested against observations. When physicists and astronomers look at the cosmic microwave background radiation in detail, not just its average temperature, but the tiny temperature variations across the sky, they find exactly the pattern of fluctuations that inflation predicts. The temperature map of the cosmic microwave background is an imprint of the quantum fluctuations of the inflationary era, stretched to cosmic scales and preserved across 13.8 billion years of cosmic evolution. You can look at a map of the cosmic microwave background. The satellite missions COBE, WMAP, and Planck have produced increasingly detailed versions of it, and you are seeing the quantum fingerprint of the first trillionth of a trillionth of a trillionth of a second stretched across the entire sky. The universe has preserved, in its oldest and most uniform light, the memory of its own quantum origins. Let us step back from the physics for a moment and simply sit with what we have established. The universe began approximately 13.8 billion years ago from a state of extraordinary density and temperature. In the first fractions of a second, it underwent a period of exponential expansion called inflation that smoothed its geometry, established its uniformity, and planted the tiny quantum seeds from which all structure would eventually grow. In the first microsecond, the quarks and gluons of the quark-gluon plasma condensed into protons and neutrons. In the first second, the matter-antimatter asymmetry led to the survival of a tiny residual excess of matter, 1 part in a billion, that became everything. In the first few minutes, nuclear fusion in the hot, dense plasma produced the first atomic nuclei, hydrogen and helium, in the proportions we still observe today. All of this happened in the first 3 minutes. 3 minutes. The entire chemical, the foundation of the universe, the ratio of hydrogen to helium, the abundance of deuterium, the trace amounts of lithium was established in the first 3 minutes. The large-scale geometry of the universe, its flatness, its uniformity, the statistical properties of its density fluctuations was established in an even smaller fraction of that time. The fundamental particles from which all matter is built were produced in the first microsecond. 3 minutes of physics set the parameters for 13.8 billion years of cosmic evolution. After 3 minutes, the universe had the raw materials, hydrogen, helium, a tiny bit of lithium, and the initial conditions, a slightly lumpy, expanding, cooling plasma from which everything else would grow. But the growth was not immediate. The universe still had hundreds of thousands of years of simpler, quieter physics ahead of it before the first atoms could form. The universe is 3 minutes old. The nuclear reactions that built the first atomic nuclei are over. The universe is now a plasma, a hot, dense mixture of protons, helium nuclei, electrons, photons, and neutrinos, all interacting with each other. The photons bouncing off the charged particles in every direction. The universe opaque to light in the way that the interior of a star is opaque to light. This state will persist for a very long time, for 380,000 years. 380,000 years is an enormous span of time, by human standards, more than 50 times the entire duration of recorded human civilization. And yet in the 13.8 billion year history of the universe, it is the opening chapter, less than 0.03% of the total. During these 380,000 years, the universe is expanding and cooling, but relatively little is changing in terms of the types of particles and interactions present. The photons bounce off electrons, the electrons bounce off photons and nuclei. The whole dense plasma churns and interacts in a state of near-perfect thermodynamic equilibrium. Temperature and pressure and density are all slowly decreasing as the expansion proceeds. But the fundamental nature of what the universe contains is stable. Then, At 380,000 years, the temperature drops below approximately 3,000 degrees, and something happens that cosmologists call recombination. At 3,000 degrees, the energy of the photons is low enough that they can no longer ionize hydrogen atoms as fast as electrons combine with protons. The universe crosses a threshold. The electrons can now stay attached to protons, forming neutral hydrogen atoms without being immediately stripped away by photons. In a geological instant, over a period of perhaps 100,000 years, which is brief, on cosmological scales, the universe transitions from a plasma of free electrons and nuclei to a gas of neutral atoms. Neutral atoms do not interact with photons nearly as efficiently as free electrons do. Once the electrons have combined with the nuclei, the photons that fill the universe are no longer bouncing off charged particles at every step. They begin to travel freely. The universe becomes transparent. The photons that were released at the moment of recombination, the photons that, for the first time in the history of the universe, could travel freely without being immediately scattered, are still traveling today. They fill all of space, a uniform bath of microwave radiation coming from every direction in equal amounts. They are the cosmic microwave background, the afterglow of the Big Bang, and they are the oldest light in the universe. The cosmic microwave background was predicted theoretically before it was discovered observationally. In 1948, the physicists Ralph Alpher and Robert Herman, working with George Gamow, predicted that if the universe began hot and dense, the radiation from the hot early universe should still be present today, cooled by the expansion to a temperature of about 5 degrees above absolute zero. The prediction was largely ignored for nearly 2 decades. In 1965, 2 radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Labs in New Jersey, trying to calibrate it for radio astronomy. They kept detecting a persistent noise in their measurements, a faint, uniform microwave signal coming from every direction in the sky that they could not eliminate regardless of what they did. They checked their equipment. They removed a pair of pigeons that had nested in the antenna and cleaned out the pigeon droppings. The signal persisted. Eventually, they connected with physicists at Princeton who were independently working on the theoretical prediction of exactly such a signal. The physicists at Princeton were, in fact, in the process of building an instrument to detect it. Penzias and Wilson had already found it by accident. The cosmic microwave background is real. It has been mapped in extraordinary detail by 3 generations of satellite missions. Its temperature is 2.725 degrees, above absolute zero, uniform to better than 1 part in 100,000. The tiny temperature variations, the 1 in 100,000 fluctuations, match with extraordinary precision the predictions of inflationary cosmology and Big Bang nucleosynthesis. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery of the cosmic microwave background. What they had found, without looking for it, was the oldest light in the universe. The light released 13.8 billion years ago when the universe first became transparent, cooled by the expansion of space from the 3,000 degrees of recombination to the 2.7 degrees of the present day. A photograph of the universe at 380,000 years old, taken from every direction simultaneously, preserved in the microwave glow that fills all of space. The universe is transparent. The cosmic microwave background has been released. The universe is now a vast, expanding, cooling gas of neutral hydrogen and helium, seeded with the tiny density fluctuations planted by the inflationary era. What happens next is both simple and slow. The simple part is gravity. Gravity is, of all the forces, the simplest in its behavior on large scales. It is always attractive. It acts over unlimited distances, and it grows stronger as more mass is concentrated in one place. Gravity does not care about the chemical complexity of what it acts on. or the temperature, or the state of aggregation. It simply pulls matter toward matter. The regions of the early universe that are very slightly denser than average, the temperature fluctuations in the cosmic microwave background are the fingerprint of these density variations, attract slightly more matter than the surrounding regions. Over time, very long times, the slightly denser regions become denser still as they pull in more matter, while the slightly less dense regions become emptier. The tiny initial fluctuations of 1 part in 100,000 are amplified over hundreds of millions of years into the structures we see today. This is the simple part. The slow part is the time scale. After recombination, the universe is extremely smooth. Those 1 in 100,000 fluctuations are genuinely tiny. Growing them into the first stars and galaxies takes time, a lot of time. For the first roughly 100 million years after the Big Bang, the period that cosmologists call the Cosmic Dark Ages, the universe contains no light sources. The cosmic microwave background photons are still present, but they are cooling and redshifting, their energy declining, the universe gradually growing darker. The hydrogen and helium gas is expanding and cooling, slowly but inexorably gravitating into the overdense regions that will eventually become the first galaxies. The Dark Ages are exactly what they sound like: dark, cold, silent. A universe of expanding gas and microwave background radiation, with no stars, no light, no chemical complexity, no structure except the slowly growing density waves planted by inflation. This is perhaps the longest, quietest chapter in the history of the universe. For 100 million years, the universe expanded and cooled, and nothing that we would call interesting happened. The gas fell slowly toward the centers of the overdense regions. The density in those regions grew slowly higher. Slowly, imperceptibly, in each of those overdense regions, the gas was being compressed toward the conditions that would eventually trigger nuclear fusion. At some point, approximately 100 to 150 million years after the Big Bang, though the precise timing is uncertain and is one of the active research questions in observational cosmology, the first stars formed. The first stars were nothing like the stars we know. The contemporary universe contains stars in an enormous range of sizes, from red dwarf stars, barely large enough to sustain nuclear fusion, to massive blue giants, 100 times the mass of the Sunday. They are composed of a mixture of hydrogen and helium, enriched by the heavier elements, the metals, as astronomers call anything heavier than helium produced by previous generations of stars. The first stars were formed from pristine primordial gas, pure hydrogen and helium, with none of the heavier elements that subsequent stellar generations would produce. This makes a significant difference. The cooling of gas is one of the key processes that allows a collapsing gas cloud to form a star rather than simply heating up and resisting further collapse. In the contemporary universe, gas clouds cool efficiently because they contain molecules and dust grains made of heavier elements, which are very effective at radiating away the heat of compression. In the primordial universe, the gas contained only hydrogen and helium, which are far less efficient coolants. The consequence is that the first stars were, almost certainly, very massive. The primordial gas clouds had to grow much larger before they could cool efficiently enough to collapse into stars, and larger gas clouds produce more massive stars. The first stars, called Population 3 stars by astronomers, a name that reflects the historical classification in reverse order, were probably on average tens of times more massive than the Sun, and perhaps hundreds of times more massive in the extreme cases. Massive stars burn their nuclear fuel fast and die young. A star like the Sun will live for approximately 10 billion years, fusing hydrogen to helium in its core for billions of years before its demise. A star 100 times the mass of the Sun will exhaust its nuclear fuel in only a few million years. The first stars were short-lived, brilliant, and violent in their deaths. And their deaths mattered enormously for everything that followed. When a massive star exhausts its nuclear fuel, Its core collapses under gravity in a fraction of a second, triggering a catastrophic explosion called a supernova. The supernova releases more energy in that fraction of a second than the Sun will release in its entire 10 billion year lifetime. The outer layers of the star are blasted into space at a fraction of the speed of light. And those outer layers contain something new, something the universe had never had before. The cores of the first massive stars were factories for nuclear fusion. As a star evolves, it fuses progressively heavier elements, hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to silicon, silicon to iron. Iron is the end of the road. Iron cannot be fused to release energy. And when the iron core of a massive star grows too large, the collapse and explosion that follows is inevitable. But all of the elements produced in that stellar core, carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, iron, are blasted into the surrounding gas when the star explodes. Mixed with the primordial hydrogen and helium, these new elements seed the next generation of gas clouds, with the raw material for a more complex chemistry. The second generation of stars, population 2 stars, forms from this enriched gas. They are still predominantly hydrogen and helium, but they contain trace amounts of carbon and oxygen and silicon and iron. These trace amounts make an enormous difference to the chemistry of their planetary systems, if they form any, and to the biology that might eventually arise in those systems. The third generation, population I stars, our Sun among them, forms from gas enriched by multiple generations of stellar processing. Their composition includes a few percent of elements heavier than helium, enough to build rocky planets, to build water, to build the organic molecules that are the precursors of life. Every heavy element in your body was forged in the core of a star that died before our solar system formed. The calcium in your bones was fused in the shell of an old red giant star. The oxygen you breathe was produced in the cores of massive stars and distributed by their supernovae. The iron in your blood was synthesized in a stellar core and expelled into space in an explosion that briefly outshone an entire galaxy. We are, in the most literal possible sense, made of stardust, not as poetry, as chemistry. The first stars form. They live their brief, brilliant, violent lives. They die and scatter their heavy element gifts into the surrounding gas. The gas, enriched, cools more efficiently, collapses more readily, forms the next generation of stars in greater numbers and with a wider range of masses. And simultaneously, the large-scale structure of the universe is continuing to develop. The density fluctuations planted by inflation are growing under the influence of gravity. But they are not growing uniformly. Something is helping gravity, something that we can detect through its gravitational effects, but have never directly observed, what physicists call dark matter. Dark matter is one of the deepest mysteries in contemporary physics. The evidence for its existence is overwhelming and comes from multiple independent sources: the rotation curves of galaxies, the gravitational lensing of light around galaxy clusters, the large-scale structure of the cosmic web, the details of the cosmic microwave background. All of these observations require the presence of significantly more mass than is accounted for by the ordinary matter, the hydrogen and helium and heavier elements that we can see. The extra mass is approximately 5 times as abundant as ordinary matter. It does not interact with electromagnetic radiation. It does not emit light, absorb light, or reflect light. It is invisible in every wavelength. It interacts with gravity, and it may interact through the weak nuclear force, but it does not interact electromagnetically, which is why we cannot see it. We do not know what dark matter is. The leading candidates include particles called WIMPs, weakly interacting massive particles, and axions, both predicted by extensions of the Standard Model of particle physics, and both searched for extensively in experiments around the world without being definitively detected. There are also more exotic possibilities. There is even a school of thought that questions whether dark matter is a substance at all, perhaps. Some physicists argue our theory of gravity is wrong on large scales, and what we are interpreting as dark matter is actually a modification of how gravity works. But most evidence points toward dark matter being real, being some kind of particle that interacts gravitationally but not electromagnetically. In the early universe, dark matter played a crucial role. Because it does not interact electromagnetically, it was not coupled to the photon-baryon plasma in the way that ordinary matter was. It could begin to clump under gravity even before recombination, while ordinary matter was still trapped in the plasma and unable to fall into the dark matter's gravitational wells. By the time recombination occurred and ordinary matter was released from the plasma, the dark matter had already assembled into a network of filaments and halos, the skeleton of the cosmic web. The ordinary matter, the hydrogen and helium, fell into the gravitational wells that the dark matter had prepared. The first galaxies formed at the nodes of this dark matter web, where the filaments intersected and the concentration of dark matter, and therefore the gravitational attraction, was greatest. The large-scale structure of the universe, the cosmic web, the great filaments of galaxies stretching across hundreds of millions of light years, the voids between them nearly empty of matter. The clusters at the intersections of the filaments containing thousands of galaxies each is a visible tracing of the dark matter skeleton that assembled in the first billion years of cosmic history. The ordinary matter went where the dark matter told it to go. 1 billion years after the Big Bang, the universe looks very different from what it was at 380,000 years. The cosmic dark ages are over. The first stars have formed, lived, and died, seeding the universe with the first heavy elements. The second generation of stars is forming in the first galaxies, small, irregular collections of stars and gas, nothing like the grand spiral and elliptical galaxies of the present day, but the beginnings of the cosmic architecture we see today. The universe is still mostly hydrogen and helium. The heavy elements are present, but in tiny traces, concentrated near the sites of stellar birth and death. Most of the volume of the universe is intergalactic space, nearly empty, cold, and dark, the vast voids of the cosmic web, expanding with the universe, growing ever larger. But structure is assembling. The small early galaxies are merging with each other, driven together by gravity, combining their stars and gas into larger and larger systems. The first galaxy clusters are forming at the nodes of the dark matter web. The filaments connecting them are carrying streams of gas that feed the growing galaxies, providing the raw material for new generations of stars. This process, the hierarchical assembly of cosmic structure, small things merging into larger things, driven by the relentless pull of gravity, is one of the most beautiful and well-confirmed aspects of cosmological theory. The simulations of cosmic structure formation, run on the world's most powerful computers, reproduce with extraordinary fidelity the actual distribution of galaxies we observe. The cosmic web that the simulations produce matches the cosmic web we map with galaxy surveys, the same patterns of filaments and voids and clusters, on the same scales, with the same statistical properties. The physics is working. 4.5 billion years after the Big Bang, roughly 9 billion years ago, something specific happens in an undistinguished region of an undistinguished galaxy, in an undistinguished part of the universe. A cloud of gas and dust, enriched by several generations of stellar processing, begins to collapse under its own gravity. This is not an unusual event. It is happening in millions of locations across the universe simultaneously. But this particular cloud, in this particular location, will produce something that matters to us specifically. The cloud collapses. At its center, the density grows high enough, and the temperature rises high enough for nuclear fusion to ignite. A star is born. It has roughly the same mass as the Sunday, It is a third-generation star, a population 1 star, enriched by the deaths of its predecessors with enough heavy elements, carbon, oxygen, silicon, iron, and dozens of others to form a system of planets around it. And it does. In the disk of gas and dust that surrounds the newly formed star, the protoplanetary disk, the standard feature of stellar formation that has been observed around hundreds of young stars with modern telescopes, the same processes of accretion that built planets in billions of other solar systems are now building planets. Here, dust grains collide and stick, pebbles accumulate, planetesimals grow, planetary embryos form and collide and merge. Within a few tens of millions of years, a system of planets has taken shape around the new star. The inner planets are rocky. Their formation region was too warm for ices to be stable, so they are built from silicates and metals. The outer planets are gas and ice giants far enough from the star that water ice could be incorporated into the growing planetary bodies, giving them the volatile inventories that the inner planets lack. The third rocky planet from the star forms and cools and eventually develops an ocean, and the ocean develops life, and the life develops complexity, and the complexity develops consciousness, and the consciousness wonders about its origins. We have been here before, in other journeys. We know this story. We know the ocean before it had life, and the billion years of chemistry that preceded the first cell, and the 4 billion years of biological evolution that led from that first cell to the present moment. What we did not know, until this journey, is what preceded the ocean, what preceded the Earth, what preceded the solar system, what preceded the galaxy, what preceded the universe itself. Now we know. Or rather, now we know as much as science has been able to determine, and we know where the knowledge ends and the honest uncertainty begins, and we know that the honest uncertainty is not a failure of science, but a frontier that is still being explored. Let us talk about what we do not know, because the things we do not know are at least as important as the things we do, and intellectual honesty requires acknowledging both. We do not know what happened before the Big Bang, if anything. The laws of physics, as we currently understand them, break down at the Planck time, leaving us without the theoretical tools to describe what preceded it. Some physicists argue that the question is meaningless, that since time began at the Big Bang, asking what came before it is like asking what is north of the North Pole. Others argue that the Planck era must itself have emerged from something, some prior state that our incomplete physics cannot yet describe. There are speculative theories. The eternal inflation hypothesis suggests that our universe is one bubble in an eternally inflating cosmic foam, one of perhaps infinitely many universes that have nucleated from the inflating background. In this picture, the Big Bang of our universe is a local event in a much larger, perhaps infinite cosmos that had no beginning. The loop quantum cosmology approach suggests that the Big Bang was a bounce that the universe contracted from a previous state, reaching a maximum density described by quantum gravity, and then rebounded into the expansion we observe. In this picture, there was something before the Big Bang, a contracting universe that preceded the current expanding one. The cyclic model proposes an oscillating universe, cycles of expansion and contraction repeating indefinitely. Each Big Bang, the beginning of a new cycle, and the end of the previous one. String theory and its various descendants suggest the possibility of a landscape of possible universes, a vast ensemble of different physical laws and constants, of which our universe with its specific parameters is just one. None of these ideas is confirmed. None of them, yet, makes predictions that can be tested and distinguished from the alternatives with available observations. They are hypotheses, scaffolding for thinking about questions that may eventually become answerable as our theoretical and observational tools improve. They may point toward the truth, or they may all be wrong. We do not know. We also do not know what dark matter is. We have known of its gravitational effects for decades. we have never detected a dark matter particle directly. The experiments designed to detect WIMPs placed deep underground to shield them from cosmic ray backgrounds, using detectors made of increasingly exotic and sensitive materials, have not found what they were looking for. Either dark matter is not WIMPs, or WIMPs are lighter or interact more weakly than the models predicted, or the experiments are not yet sensitive enough. We also do not understand dark energy. In 1998, two teams of astronomers independently discovered something remarkable and deeply puzzling. They were measuring the distances and recession velocities of distant supernovae exploding stars, whose intrinsic brightness is well understood and can therefore be used as standard candles to measure cosmic distances, and they expected to find that the expansion of the universe was slowing down. Gravity should be pulling the galaxies back toward each other, slowing the rate of expansion over time. Instead, they found that the expansion is accelerating. The universe is not just expanding, it is expanding faster and faster. Something is pushing space apart, counteracting gravity on the largest scales, causing the expansion to speed up rather than slow down. The name given to this something is dark energy, and it makes up approximately 68% of the total energy density of the universe. Ordinary matter, everything we can see, everything we have ever touched, all the stars and galaxies and gas clouds makes up only about 5%. Dark matter makes up about 27%. We are made of the rarest constituent of the universe. The atoms in your body, ordinary matter, the matter described by the standard model of particle physics, are a minority constituent of a universe whose dominant components we do not understand. The nature of dark energy is one of the deepest unsolved problems in physics. The simplest explanation that it is the energy of empty space itself, the cosmological constant that Einstein introduced and later abandoned, restored to its original role by the discovery of the accelerating expansion, fits the observations well. But it creates a profound puzzle. Quantum field theory predicts a vacuum energy density that is roughly 120 orders of magnitude larger than the observed dark energy density. The gap between the theoretical prediction and the observed value is the largest discrepancy between theory and observation in the history of physics. Something is deeply wrong with either our theory of dark energy or our understanding of the quantum vacuum, and we do not know what. Dark energy, dark matter, the physics before the Planck time, the mechanism of baryogenesis. These are the major unknowns of fundamental cosmology. They are significant. They point to the incompleteness of our understanding. But they do not undermine what we do know. The Big Bang happened. The universe is 13.8 billion years old. It expanded from a hot, dense state. The light elements were produced in the first few minutes. The cosmic microwave background is real, and its properties match the predictions of the theory with extraordinary precision. The large-scale structure of the universe developed as the theory describes. We know a great deal, and we know that we do not know everything. Both of these are true simultaneously, and both matter. Let us talk about the fate of the universe. Where is all of this going? Where does the story end? If dark energy remains constant, if the energy density of empty space remains what it is today, as the universe expands, then the universe's future is one of progressive isolation. As the expansion accelerates, galaxies that are currently separated by distances that light can bridge in a finite time will eventually be moving apart faster than light can travel between them. They will cross what cosmologists call the cosmic horizon, the boundary beyond which no signal from us can ever reach, and no signal from them can ever reach us. In the very distant future, hundreds of billions of years from now, the expansion will have driven every other galaxy beyond our cosmic horizon. The Milky Way and its closest neighbors, the Andromeda Galaxy, and the other members of the local group, will have merged into a single giant elliptical galaxy, the wreckage of their collision preserved in the mingled stars. But every other galaxy, every other cluster, every other structure in the universe will have retreated beyond the horizon, invisible, unreachable, effectively non-existent from our perspective. In the very, very distant future, trillions of years from now, even the stars within our merged local group will have burned out. The longest-lived stars, the red dwarfs, will continue to fuse hydrogen for trillions of years, but eventually even they will exhaust their fuel. The stellar populations of the universe will decline over timescales of tens of trillions of years, as stars die and the remaining gas is consumed or dispersed. After the stars go dark, what remains is white dwarfs, neutron stars, and black holes. The white dwarfs will cool over unimaginably long timescales, from glowing embers to cold dark objects called black dwarfs. The neutron stars will cool similarly. The black holes will remain, consuming what they can, growing slowly larger. But even black holes are not eternal. The physicist Stephen Hawking showed in 1974 that black holes are not perfectly black. They emit a faint quantum radiation called Hawking radiation, which causes them to slowly lose mass and eventually evaporate. The timescale for a stellar mass black hole to evaporate via Hawking radiation is approximately 10 to the 67th years, a number so large that it makes the current age of the universe look like an instant. But even that number is finite. Eventually, even the black holes are gone. What is left after the last black hole has evaporated after 10 to the 100th years have passed? A number that has no intuitive meaning but is finite, is a universe of cold, dilute particles, electrons, positrons, photons, and neutrinos, expanding through an increasingly cold and dark and empty void. If protons are unstable, if they eventually decay, as some grand unified theories predict, then even the matter in the white dwarfs and black dwarfs will eventually dissolve into radiation, on timescales of perhaps 10 to the 40 years. The final state of the universe, if dark energy remains constant, and if the laws of physics as we understand them remain valid on these unimaginable timescales, is what physicists call heat death, a state of maximum entropy, in which all energy is uniformly distributed, no temperature gradients exist to drive any process, and nothing of what we would recognize as structure or complexity persists. This prospect, the heat death of the universe, the end of all structure, all chemistry, all biology, all thought is sometimes experienced as deeply melancholy. It can seem like a repudiation of the significance of everything that has happened. 13.8 billion years of cosmic evolution, billions of years of biological evolution, the emergence of consciousness and civilization, and everything that consciousness and civilization have produced, all of it eventually lost in the cold, uniform dark. But there is another way to hold this thought, and it requires only a small shift of perspective. The universe is not over yet. It is, in terms of the time scales we have been discussing, extraordinarily young. The current age of the universe, 13.8 billion years, is a tiny fraction of the timescales on which the universe will continue to evolve and change. The stars are still burning. The galaxies are still forming. The conditions for life exist, today, in an enormous number of places across the observable universe. The story is not finished, and the fact that it will, eventually, and that even the cosmos has a finite duration does not diminish what has happened in it. The fact that a piece of music ends does not retroactively drain the music of its beauty. The fact that a life is finite does not make the life meaningless. If anything, finitude is the condition that makes meaning possible, because meaning requires context, requires contrast, requires the possibility that things might have been otherwise. The universe had a beginning, it will have an end. Between those two events, it produced matter from energy, stars from gas, planets from dust, life from chemistry, and minds from biology. It produced the specific configuration of matter and energy that you are, here, now, in this moment, aware of its own origins and contemplating its own fate. That is not nothing. That is, perhaps, everything. We have traveled far tonight. Let us trace the path we have taken. We began before the beginning, in the nothing that preceded the universe, a nothing so complete that the concept of nothing barely applies, because even the absence of things requires space and time in which things could be absent. We established that the universe began approximately 13.8 billion years ago from a state of extraordinary density and temperature, not an explosion in space, but an expansion of space itself, carrying matter and energy with it from the very first instant. We explored the first fraction of a second, the Planck era, where our physics breaks down and we cannot see clearly, the inflationary era, where the universe underwent exponential expansion, smoothing its geometry and planting the seeds of all future structure, the quark-gluon plasma, where matter as we know it first appeared, the matter-antimatter asymmetry, where the tiny imbalance that allowed everything to exist was established, and the first microsecond, where quarks condensed into protons and neutrons. We watched the first 3 minutes, where Big Bang nucleosynthesis produced the hydrogen and helium that make up the bulk of the universe's matter, in the precise proportions we observe today. We followed the universe through 380,000 years of cooling plasma to the moment of recombination, when the first atoms formed and the universe became transparent, releasing the cosmic microwave background, the oldest light in the universe, still filling all of space today at a temperature of 2.7 degrees above absolute zero. We traveled through the cosmic dark ages, the first 100 million years after recombination, when the universe contained no stars and no light, only expanding gas falling slowly toward the overdense regions where the first cosmic structures would form. We watched the formation of the first stars, massive, brilliant, short-lived, nuclear furnaces that produced the first heavy elements and distributed them to the surrounding gas when they died in supernovae. We understood how each generation of stars enriched the universe with heavier elements, building the chemical complexity that eventually made rocky planets and liquid water and organic molecules possible. We discussed dark matter, the invisible, gravitationally dominant component of the universe that assembled the scaffold on which the visible structures of galaxies and galaxy clusters were built. We discussed dark energy, the mysterious constituent that makes up 68% of the universe's energy and is causing the expansion to accelerate, driving the ultimate fate of the cosmos toward the cold and empty heat death of the very distant future. We watched the formation of our own solar system, 4.5 billion years ago, from a cloud of gas and dust enriched by several generations of stellar evolution, a story we have followed through other journeys to the origin of the ocean, to the first life, to the emergence of complexity. And we considered the fate of the universe, the progressive isolation of the local group, as dark energy pushes other galaxies beyond the cosmic horizon, the eventual extinction of the stars, the slow evaporation of the black holes, and the final cold diffuse state of maximum entropy that awaits, on timescales that make the current age of the universe seem brief. This is the full sweep of cosmic history from before the beginning to after the end, with everything we know, and an honest acknowledgement of everything we do not know, laid out as clearly as the current state of physics allows. There is a thought that sits at the center of all of this, and it is perhaps the most important thought in science, and it is this: the universe did not have to be this way. The laws of physics that govern our universe, the specific values of the fundamental constants, the masses of the elementary particles, the strengths of the 4 fundamental forces, the rate of expansion of the universe, the magnitude of the density fluctuations planted by inflation are what they are, but they could, in principle, have been different. Change the strength of the strong nuclear force by a few percent, and carbon cannot form in stellar cores, and there is no chemistry of life. Change the mass of the electron slightly, and atoms cannot form stable structures. Change the cosmological constant by even a small amount, and the universe either collapses back on itself before galaxies can form or expand so rapidly that matter never has time to clump together. The universe appears, in short, to be fine-tuned for the existence of complex structures, and specifically for the existence of life and minds. This observation has generated enormous philosophical and scientific discussion because it is genuinely remarkable and genuinely puzzling. 3 broad responses have been proposed. The first is that the fine-tuning is explained by the existence of many universes, the multiverse. If there are an enormous number of universes, each with different values of the physical constants, then it is not surprising that at least some of them have constants that permit complex structures in life. We observe the constants we observe because we exist in one of the universes where the constants permit our existence. A universe with different constants would not have observers to notice its constants. This is called the anthropic argument, and it is philosophically controversial, but scientifically respectable. The second is that the fine-tuning reflects deep physical relationships that we do not yet understand, that the values of the constants are not independent and arbitrary, but are constrained by a deeper theory that we have not yet discovered. In this view, the apparent fine-tuning is the signature of a fundamental physical principle waiting to be uncovered. The development of a complete theory of quantum gravity, or a fully realized version of string theory, or some other theoretical breakthrough, might show that the constants could not have been very different from what they are. The third is that the fine-tuning reflects intentional design, that the universe was created by an intelligence with the specific goal of producing life and minds. This is the position of the major theistic religions and of certain philosophers of religion. It is not a scientific theory because it makes no testable predictions, but it is not therefore irrational. It is a philosophical or theological response to the same observation that the scientific responses address. Science does not, at present, adjudicate between these responses. The multiverse hypothesis makes predictions that are, in principle, testable in some versions. If inflation produced different observable signatures in different bubble universes, those signatures might be detectable as anomalies in the cosmic microwave background. But the tests are difficult, and the results so far ambiguous. The idea of a deeper physical theory constraining the constants is appealing, but speculative. The design hypothesis is not scientifically testable in any direct sense. What science can say is this: the universe, as we observe it, is consistent with having begun in a hot, dense state, approximately 13.8 billion years ago, and with having evolved according to physical laws that remain constant across the observable universe, in a way that has produced, over billions of years, the conditions for the existence of matter and chemistry and biology and minds. Whether those laws and those conditions are what they are by chance, by physical necessity, or by design, is a question that science cannot, at present, answer, and may never be able to answer fully. The appropriate response to this uncertainty is not to pretend it does not exist. It is to hold it honestly, to carry the question without demanding an answer that the evidence does not support, to remain open to new evidence while resisting the temptation to fill the gap with certainty that has not been earned. Let us talk about what it means to know all of this, not in the abstract, not in the general sense of how knowledge is valuable, but specifically, tonight, lying in the dark, having traveled from before the beginning to after the end and back to this moment, what does it mean to carry this knowledge? The human brain evolved to navigate a world of intermediate scales, a world of objects that can be seen and touched, of distances that can be walked, of time scales that can be experienced. The brain is extraordinarily good at navigating that world. It is not designed, it could not have been designed by natural selection to have an intuitive grasp of quantum mechanics or general relativity or the cosmological scales that we have been exploring tonight. And yet the brain can reason about these things. The same cognitive machinery that evolved to track predators and navigate forests and maintain social relationships can, with training and effort and the right mathematical tools, construct theories of the very large and the very small that make predictions accurate to 11 decimal places. The brain evolved for one purpose and discovered it could do something entirely different with the same architecture. This is one of the most remarkable things about the human mind. It vastly overpowers what evolution required of it. Natural selection needed a brain that could track animals, recognize faces, remember the locations of food sources, navigate social hierarchies, and plan for the near future. It did not need a brain that could calculate the quantum electrodynamic corrections to the electron's magnetic moment, or deduce the composition of stars from their spectra, or reconstruct the first 3 minutes of the universe from the abundance of helium and the temperature of the cosmic microwave background. And yet here we are, in possession of exactly such a brain, in a universe that has, apparently, been producing the conditions for such brains for 13.8 billion years. The universe is, in one sense, simply physics. Particles and forces and fields, evolving according to mathematical laws, without consciousness or intention or preference for any particular outcome. In this sense, the universe does not know we are here. The galaxies do not care about us. The photons of the cosmic microwave background that pass through our bodies at this very moment, traveling from the recombination surface 13.8 billion years ago, are not aware of their journey or of the minds they pass through. And yet those photons, and the physics that produced them, and the billions of years of stellar evolution that built the carbon and oxygen of our bodies, and the specific sequence of geological and biological events that produce the minds capable of understanding all of this. These things are not accidents in the sense of having been unlikely. They are accidents in the sense of not having been designed, not having been aimed at. But they are the natural consequence of physics operating over long timescales in the specific universe we inhabit. The universe produced minds, not intentionally, but actually, concretely, as a consequence of its physics. And those minds are capable of reconstructing, from the evidence available to them, the entire 13.8 billion year history of the cosmos, from before the first second to the last evaporation of the last black hole. The universe became aware of itself through us, through the specific, improbable, unrepeatable configuration of matter and chemistry and biology that produce the kind of mind that asks these questions. This is either the most important thing in the universe or merely one interesting thing among many, depending on your philosophical inclinations. But it is, at minimum, a remarkable thing. The atoms that were in the first stars are in us now, and through us they are wondering about themselves. We are almost at the end of this particular journey. But before the quiet of the night takes over fully, there is one more thing to hold. The Big Bang is not just the beginning of the universe. It is the beginning of the story you are part of. The specific hydrogen atoms in your body were forged in the first minute of the universe's existence, fused from protons in the quark-gluon plasma of the first second, surviving the matter-antimatter annihilation because of the tiny 1 in a billion asymmetry that allowed matter to exist at all, drifting through 380,000 years of opaque plasma, flowing through the cosmic dark ages as part of the expanding hydrogen gas, falling into the first overdense regions under the gravity of dark matter halos, being incorporated into the first stars, surviving their supernovae, drifting through the interstellar medium for billions of years, falling into later generations of stars, cycling through stellar interiors, and being expelled back into space, accumulating in the gas cloud that became our solar system, being incorporated into the Earth, cycling through the geological and hydrological systems of our planet for billions of years, being incorporated into the first cells, cycling through billions of generations of living things, and arriving, in the specific configuration they are in now, inside you, at this moment. That is the full journey of the atoms in your body. That is the complete biography of the substance you are made of. And it begins, without exception, at the Big Bang, at the first second of the universe's existence, in the hot, dense plasma where the hydrogen was forged. You are 13.8 billion years old. Not in the sense that your consciousness has persisted for that time. Consciousness is a recent development, measured in hundreds of thousands of years at most, but in the sense that the matter you are made of has been part of the universe for its entire existence. You are, in your substance, as old as everything. This is not a comforting thought in the conventional sense. It does not promise safety or meaning or continuity. It simply is a fact about the physical nature of what you are made of, presented not as consolation but as accuracy. But there is something in it that might work as comfort, if you let it. The universe has been doing this cycling matter through structures of increasing complexity, building organization from chaos, producing minds from matter for its entire existence. The process that produced you is not an anomaly. It is the characteristic behavior of this specific universe, the thing that this specific universe does with physics and time, and the specific values of its fundamental constants. The universe is the kind of thing that produces you. Not only you, not necessarily you specifically, with your specific thoughts and memories and sense of self, those are contingent, the product of a specific evolutionary and biographical history, but minds, the capacity for awareness and wondering, the capacity for lying in the dark and asking where everything came from. The universe is, among other things, in the business of producing that capacity. It has been doing it for at least a few 100,000 years in this part of this galaxy. It may be doing it in many other places, around many other stars, in many other galaxies, right now. We do not know. The universe is very large and very old, and we have only the most limited view of it. But we know it did it here. We know that the 13.8 billion year sequence of events from the hot, dense beginning to the present moment included, as one of its consequences, the emergence of minds capable of reconstructing that entire sequence. The universe looked back at itself. That happened. Whatever else is uncertain, whatever the nature of dark matter and dark energy, whatever preceded the Big Bang, whatever the ultimate fate of the cosmos that happened, the atoms of the Big Bang produced beings who can tell the story of the Big Bang. The room is quiet now, or it should be, if you have. Let it become what it is. The cosmic microwave background radiation is passing through you at this moment. Photons released 13.8 billion years ago from the recombination surface, cooled by the expansion of space to 2.7 degrees above absolute zero, streaming through the universe in all directions, passing through walls and air, and the matter of your body as though it is not there. You are immersed in the oldest light in the universe, and you cannot feel it, but it is there. It has always been there, since 380,000 years after the beginning, filling all of space with the uniform glow of the Big Bang's aftermath. The stars overhead, if you could see them through the ceiling, through the walls, through the layers of atmospheric air, are each one a nuclear furnace, fusing hydrogen to helium in their cores by the same process that produced the universe's hydrogen in its first minute. The light they produce has been traveling toward you for years or decades or centuries or millennia, depending on the star. And when it enters your eye, or would, if you were standing under an open sky, it brings with it information about the star's temperature and composition, information that astronomers can read in the spectrum of that light and use to reconstruct the star's history. Everything is, in this sense, information. Everything carries in it the traces of its own history. The cosmic microwave background carries the history of the Big Bang. The light from stars carries the history of stellar evolution. The rocks of the Earth carry the history of the solar system's formation. The DNA in your cells carries the history of 4 billion years of biological evolution. You are not separate from the universe's history. You are part of it. You are, in the most literal sense, the universe's history, the specific configuration of matter and energy that the 13.8 billion years of cosmic evolution has produced at this particular location. In this particular moment, the universe did not have you as its goal. It does not have goals, but you are its product, and that is a different, and in some ways, more extraordinary thing. The universe did not aim at you, but it made you anyway, as an unintended consequence of physics operating faithfully over an unimaginable span of time. That faithfulness, the reliability of the laws of physics, the consistency of the universe's behavior across 13.8 billion years and the entirety of the observable cosmos is perhaps the most trustworthy thing that exists. The laws that govern the first second still govern this moment. The physics that produce the hydrogen in your body is the same physics that keeps the electrons in orbit around the nuclei of your atoms right now. The universe is consistent. It was there before anything else was there, and it has been consistent throughout, and it is still there, still operating, still evolving, still producing the conditions for matter and chemistry and biology in minds. This is enough to rest on. Not as an argument for anything, not as a proof or a disproof of any metaphysical position, simply as a fact, the most durable fact available, the fact that the universe is there and is consistent and has been consistent long enough to produce everything. Let that be what the night holds. Let the cosmic microwave background pass through you. Let the atoms of the Big Bang, in their current configuration, be still. The universe began. Everything followed. You are the latest thing that followed. And for tonight, in this room, in this dark, in this breath, that is enough. The hydrogen in you was made before the first stars. The oxygen was made in a star that died before our solar system formed. The carbon was assembled in a stellar interior that collapsed and exploded 3 seconds of energy before its remnant became the dust cloud that became the Earth. The iron was forged at the end of a stellar lifetime that ended in a supernova bright enough to outshine its galaxy. You are the meeting place of all of this. The specific location in space and time where the products of 13.8 billion years of cosmic chemistry happen to be organized, temporarily, into a mind. The universe is enormous. It is old. It is, in most of its volume, empty and cold and without life. But in this small corner of it, around this particular star, on this particular planet, at this particular moment, the long history of cosmic evolution has produced something that can hold the whole history in its mind. The Big Bang is not ancient history. The Big Bang is the first chapter of the story you are living. Sleep now. The universe is still there. It will still be there in the morning. It was there before you, and it will be there after. And right now, tonight, it is also here in the atoms of your body, in the light passing through the air, in the gravity that holds you to the earth, in every photon and every particle and every interaction in every cell. You are not in the universe. The universe is in you. Rest.